like for instance, the syntax for ggplot, right? Ggplot means grammar of graphics, so it stands for the grammar of graphics, and there is a syntax to it. There is a language to it, right? Just like every sentence has parts of speech, noun, pronoun, etc. Every graphics has a grammar behind it, and these come as a layer, or it could be some global properties like coordinates or facets, for instance, and also scales, which are global properties of a plot. And there are some local properties like aesthetics, mappings, data. And also some of these like color. These are all forms aesthetics, right? So there is a language, there is a grammar behind the graphics, and that's what the idea behind idea behind grammar of graphics, and that's a very useful thing to know, because using that, it's a Lego block. All these things that the ggplot, the geoms, are all Lego plots, and the Lego blocks. You can use that to construct any kind of a plot that makes sense or a meaning to your data, right? So grammar of graphics is a very important topic. NAME is another analytics platform. I just have it here because you can get introduced to another thing other than R, which is a much more easier and intuitive way of doing things. And there is obviously the theory, the statistics and algorithms theory. That's a huge bunch of literature on these things. So this is give you an exposure to doing data science. Okay, so that's the idea behind having these three topics. Now, I also edited the midterm project assessment. So that is going to have the aspects of data exploration and wrangling. We have today I'm going to talk about data wrangling. Okay, so that's a very, very important part of doing data analysis. So the analysis, the whole point of doing your project is to actually wrangle the data and try to make some meaning out of it. So your midterm project, which is going to be turned in as another homework, should have the elements of the analysis that we have been discussing so far. Okay, so that's the idea. I want this project to be a continuous way of understanding. It's not like, and I don't want a project separate from homework. So that's why I want to have a comprehensive, a continuous gradation of understanding. So that's the idea behind it. So it's I edited a little bit so you can go over some of the things that's listed in here. Okay, so let's get it started. Data wrangling. It's a very important aspect of doing data analysis and data science. Most of the real world data that you get, right, it's going to be messy. Anybody try to look at the Mimic3 data, right? There are so many tables in there. So there are several missing values. There are date and time information. And so the whole idea of wrangling the data, you'll eventually work with such data when you go outside. So the whole point of doing wrangling data is to make the messier data. First of all, import the data, right? You have to first import it. It could be done by locally downloading your data set and then importing it into R, or you can actually directly import it, but that might be little, for every data set that you have, if you have several tables, it might be a bad choice to do R curl for everything. So you might as well have your data set on your computer, right? So the first thing is to do a data import of your data, and the second is actually working with the data set, making it tidy. Okay, and the third is working with multiple data tables. So that's the three important aspects that we are going to cover today. The first is importing the data, the second is tidying up the data, and the third is working with multiple tables. Okay. So a note on tables. We saw that already what a table is like. It's just like a data frame, but it's much more, it's concise. It's made in such a way that it's easier for us to manipulate data, right? A table is a form of table. But it's been refined to, it has a refined print method that shows only the first few rows, like the 10 rows, right? So just like this, once you have a table, you can list it as a table. Otherwise, in your R markdown file, if you're just going to print out, it's going to print out several tons of pages, right? So you always use table to just have a glance at your data. And just like what we had in in a data frame to access the variable, we can use a dot placeholder when we use table. For instance, dot dollar symbol A1C would give you the hemoglobin levels, right? So it will subset. So you can use this placeholder when you're using tables. Just like how without tables you can just use the dollar, but this placeholder. But for table you have to use this placeholder, the period placeholder for accessing it. And also there is an options in tables where you can print the number of rows that you want. You can have a minimum of 7 rows. I mean, I have given 7. You can have any number of rows to be printed. And that is given by this options keyword that can limit the number of data that you see. For instance, here, I'm just printing out 7 values using a table with options print min equals 7. It's going to print 7 rows in here. Okay. So now we will come into data importing. Usually most of these files, I mean, there are several ways that R can import. You can import data into R, right? I mean, there is one easier method. You go into R and then just click some button on import data set. It's going to automatically recognize and import it. But we can also do it through this read.csv, which is a comma separated value reader. It's inbuilt in R. And here I'm importing the original Haynes data set, and then I'm displaying it. So we can use this read.csv to import the data into R. Okay, there are other things that I don't want to go about, but mostly we will be working with the CSV. Even if you have in other formats, you import it into R through your regular console, through your regular interface, and then you can convert it into CSV and save it. And parsing a vector, and there is a special keyword for parsing a vector. It's called parse logical or parse integer or parse date. Okay, so most of these vectors that you can be parsed. This is specific to the dplyr. So these are things that's inbuilt in here. So for instance, here I have a logical vector consisting of true, false, and NA, and you can parse this using this parse vector, and that's going to give the labels in here, the levels in here, right? I mean, this is a logical vector, and then the integer and the date. Okay, we can also, one of the good things about parsing is we can specify if we don't want to consider a particular value as NA, we can specify that. For instance, in this Haynes data set, in the education, I think there are 2-3 levels. The number 2 is high school, I think. So I wish to denote all high schoolers as NA. You can use parse integer, and then you can specify NA equals 2. So that it's all these values. The first one was 2, and it's going to substitute NA in there. So this is a very useful function. So if parsing fails, for instance, if you have an integer and you are parsing it as a logical, right, it's going to throw out a warning saying that this is a problem. So there are so many parsing problems in here, which can be found out using problems function. There is a function called problems. So you can use problems function to see what exactly is the problem. Rather than displaying it in here, it's going to give you in a nice table format saying that it's expected these values for logicals, either 0, 1, true, false, or true or false, but it got actually 2, 3, these integer values. And so these problems can help you in troubleshooting the data, right? So parsing a different number of formats are important, right? I mean, because that can come, your data can come in several ways. Like people write numbers in a different way, right? In some countries they use period, some countries they use comma, etc., etc. And also there are some numbers, right? I mean, for instance, in dollar symbol or percentage, I mean, you may want to exclude all this if you're interested in just looking at the numbers, right? And also numbers contain grouping characters. Like for instance, here 1 million is written like this, and in some countries the grouping is done in a different way, right? So the first problem is solved by what is known as an argument local in parse double. So this parse double is going to parse it as a double. So for instance here, right, parse the number 1, 2, 3, where the decimal mark is written as comma, right? So in that case, you can pass this local argument. And then, or you can use what is known as parse number, which can just parse the number and leaving out all the symbol with this number, all right? So here, for instance, 60%, you can just parse the number. The third actually is you can use both local and also the grouping character, right? I mean, so you can use this. You can use this as a combination. You can parse the number and saying that, okay, here is a period, so just parse in that. So you will get all the values instead of it. I mean, it's useful to do that. I mean, most of the times when you have all these numbers and stuff like that, it's just makes sense to formatting the data is as important as analyzing. Okay, getting into a good tidy format where you can analyze the data is it's very important, right? And also most of the data set are stored with encoding. For instance, if you look at genomics data, FASTA, who all know here FASTA formats, right? Everybody would know here, right? I mean, this is an encoding, right? Or the SAM format, right? SAM and BAM files. What are they? What is a BAM file? What is a SAM file?
SAM files, binary version of SAM file.
Right. Yeah.
SAM file storing, read.
Right. So, I mean, basically, if you look at the genome, it's ACTG, right? So you just need to store 2 variables, right? And it can be stored in a binary format, and it's much more portable and accessible. So whenever you want to look at the data, the machine can actually immediately compute and then display to you, like just like images, like in image processing. Image is a matrix. And so what is JPEG? For instance, or all these compression form, right? I mean, it's a compression format, right? So you can store it and you can port it just using some smaller amount of numbers, so the computer can actually do the computation and show the picture to you, right? So all these are all encodings. It comes under encoding, and in R, each hexadecimal number stores a byte of information. Like 48 is H, 61 is A, etc., etc. And so this mapping of an hexadecimal number to a character is encoding. Okay, so and in the case of a standard, it's called ASCII, right? American Standard Code of mapping, right? So this function, character to raw, actually will list the encoding of characters in the ASCII format. For instance, you have this is a nice day, and if you translate it into the raw format, into the hexadecimal format, it's going to list all these vector of numbers, right? So but we need these encodings not just for English and for other languages as well. Well, fortunately, there is a nice encoding called UTF format that can encode just about any other characters and even some symbols, right? So we can parse such encodings through what is known as a parse characters. So parse character, this would actually parse. I'm giving 2 characters here or string here and asking to parse character without knowing the encoding. So I can use this map function called guess encoding, and then I'm asking it to parse it, and so it immediately is able to parse it. So that's so even if you don't know the encoding, it can give you the encoding and parse it. So that's a very powerful feature of some of these things. I mean, you may wonder where you might use it, but it can be really handy in some of the data sets. So we see that this, when you parse the second character, right? It's a Russian, actually. It's a version of a Russian alphabet. Not just that, parsing date and time is very important. So for instance, Mimic 3 has tons and tons of data with date and time information. If you look at any of those chart events, it's lots of data with date and time information, right? So there are 3 main functions for parsing date and times. One is parse date time. So that's one function which actually parses. If you have both date and time, this can parse it, but it expects in a ISO this format. So this is a standard international format for date, and this is organized by year, month, day, hour, minute, and second. Okay, so there are several versions of this formats, and you have to somehow understand or know what exactly the format of the data stored in, right? So parse date time is one format. It's one of the functions that can parse your data, and parse date. This expects a 4-digit year, okay, or a month and then a date. So this is just a standard format, and parse time, it expects hour, minutes, and optionally seconds. Okay, so for instance, if you have this 2010-10 blah 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 and this one, if you say parse date and time, it's going to parse it, and then it's going to say that okay, this is in the UTC format, right, universal time format. And also you can, if you say parse date and give it a date, you can it automatically gives it. I mean, if the defaults doesn't work, there are several options to do it. So for instance, you can specify %y, capital Y for 4 digits, %small y for 2 digits, etc., etc. So for instance here, right, you have a parse date, and I have a 0, 1, and then I say that okay, this is the format that I know, parse it in this order and this fashion, so it's going to parse it according to that way, right? And in fact, you can even set the local option to specify the different inbuilt language. For instance, if you have a French, I think this is it's they write it as January 2015, and it's going to parse it in the local language. So it's a very powerful function, parse date. So parser, right? Parser is a very useful function. You can use it for almost all vectors. So I'm not going to go over section 11.4 and 11.5. This is parsing a file and writing to a file. Most of these things could be done in RStudio without even you have to worry about it. So I'm not going to do with it. But what is critically important is dealing with dates and times. I mean, so far we have used three main features, three main functions: parse date time, parse date, and parse time. But that's not enough actually. So it can be a very tough job. Like for instance, in Mimic 3, right, I tried to use some of these functions and it didn't work actually. So Mimic 3 says that actually there is another problem in Mimic 3. Have you looked at the Mimic 3 dataset? It's all dates in 2100 to 2200. Okay, so if you go back to the original paper, they say that dates were shifted into the future by a random offset. So resulting in days sometime 2100 and 2200. So don't freak out looking at the crazy numbers in there, okay? So I tried to import this data set, okay, and see that if they import as and they didn't import as a factor, and then I used the parse date, right? So for instance, I used on this read CSV the Mimic 3 data set. So from here on, we would be dealing with a Mimic 3 data set, and try to parse date, right? And I tried to do a head, like look at the first view in this format, year, month, and date, and that's what I thought the time was, right? But I still ended up the admission time, it didn't factor. It didn't, I mean, it was still in factor, and it was not parsed at a date. So that's when actually another helpers are designed for this whole doing the data analysis. I mean, these parse date time, I think it's already inbuilt in R, but this is specifically, there is a library called lubridate. Okay, so they automatically work out the format once we specify the order of the component. Okay, so for to use them, we have to identify in which order it is. Like for instance, our starts with, if you look at the data, it starts with year, date, and year, month, and date, I think. So we have to arrange it Y, M, and D in the same order. So it will immediately parse it. Okay. So this gives the so what we have to do it is we have to load the lubridate library. So I use the lubridate library here, and then passed YMD of Mimic 3 of the admission time. Okay, so I just wanted to parse it, and it perfectly worked. I mean, it changed the factor into date format. So if you're, I mean, if sometimes if the date time didn't work, you may have to use the lubridate, and I would suggest using this lubridate because I think they have been specifically designed for dealing with such problems and inconsistencies. Okay, and we also see the discharge time, right? This is the admission time. But if you look at the discharge time, this has both admission date as well as admission time here, right? So we can use actually the parse date time function to convert from a factor data. So I tried to use the parse date time here, and it worked out perfectly fine for the discharge time. It gave me in what is known as a Unix system format. It's already there is a format, the Unix system format, that stores their data. So I mean, most of these data you never know how they have been entered, and this is how messy things, from the external data. I mean, that is why tidying up is very important, and some of these functions are inbuilt. But then fortunately for this discharge time, this date time worked, and you see that it is more in line with the format, but then it's not in the same format as this is a POSIX format. That's a Unix systems format. Okay, so sometimes we may just want to work with dates in the date time format, right? So for that we can just use as date to extract just the date. So once I have it here, I have the date and time format, I can use as date and then extract just the date here. I don't want the time actually. I mean, time is too. We are not going to be too concerned with the time, for at least for in this data set, right? So here what I'm trying to do is I'm trying to convert, just remove the time aspect of it and then keep the date here and as date, and it perfectly works. And we have the admission ID, hospital admission ID, admission time, and the discharge time. Okay, so this is a nice table format that we have that we can work with. One of the things that we noted above, right, in Mimic 3, the dates were shifted. So to make sense, it might be worth to convert the dates to earlier dates, right? I mean, to 19,000 to at least 1900 to 2000, right? So we may have to systematically convert the dates, and we can make use of what is known as time spans. Okay, so these are three powerful classes that's already inbuilt in R, right? Especially in this library. One is the durations, which represents exact number of seconds. Okay, so if you have a duration, it will give you exact number of seconds, and there is periods and there is intervals. Okay, so periods are just representing human units like weeks and months. Durations are systems based, and intervals represent a starting point and an ending point. There's a difference. We will go over that. So when we subtract two dates, there is a special object that's inbuilt called diff time. Like for instance, here you have I have this year, this discharge time, and I'm subtracting the admission time. I want to see how long a patient spent in the hospital, right? So you can subtract the discharge time minus the admission time and see how much time the patient spent in the hospital, right? So you can look at this data, and you can see that immediately it gives the format in 5 days, 7 days, and etc. etc. So this is in the human readable format that automatically converts and gives me that. So this may be one of the important features that you may use it. And actually, I wanted to see the frequency distribution. How does it vary? Like, how does it vary? These patients, the time they spent in hospital, right? So I make it as a bin width, and then I see the hospital, and I have a nice distribution. So you can see that most of the people spent about 10 days or something in the hospital, right? So this is the information that you can get. So, but then time difference can be a little painful to work when we are dealing with durations, because duration sometimes gives in seconds, right? So for instance, here I'm just converting into durations rather than looking into just the days. You can look it as a duration, right, in which you will get it in the seconds. By default, it doesn't use duration, but if you convert it, right, time spent in seconds as duration, it's going to give me the time spent in duration. It's also going to be approximately what converted into the period information. Okay, so durations come with a bunch of convenient constructors. You can say d seconds of 15. It's going to list the duration in 15 seconds. D minutes, d hours, etc., etc. So it's going to convert, and everything is going to be given in seconds. For instance, if you say d days 0 to 5, it's going to list the duration in 3 weeks. This is from 0 to 5 days, right? And if you want to list the duration in 3 weeks, you say d 3 weeks, and it's going to give you how many seconds are there. I mean, this can be useful in some of the problems, but in general, what is useful for us is periods. Actually, we have to subtract 200 years from our data set, right, to make it more meaningful, right? So that's where actually periods come. They are like time spans, but they don't have a fixed length in seconds, right? I mean, they work with human times, like 5 days and things like that. So for instance, in our you can say seconds of 15, it's going to put it as 15, right? And minutes of 10, it's just going to be, it's just all these are all in human readable formats, right? Seconds, minutes, hours, days, etc., etc. So in our data set, we can multiply periods and add them to days, right? So we can subtract 200-year time period from our admission time and discharge time. So that's what I'm doing here. I'm taking the mimic data. I am forming a new variable, admission time minus 200. So I'm taking the year, month, date of admission time and subtracting 200 from here. Okay, so just subtract 200 years from here, and so I will have the discharge time. This is the admissions time, and also I can do it for the discharge time to make it more, I mean 200 years, right? And then I can select everything. So when you do that, you have a nice table here, a table, and you have 1950s. See, it's all subtracted 200 years from it, and it gives you the admission ID, etc., etc. So I mean, this is now okay. This makes more sense to be in this span. Then we can look at the frequency of discharge over 100 period now. Okay, and from 1900s to now, you can look at what's the discharge, and you can draw by the frequency, right? I mean, so you can see that it's almost uniform, like almost all of them. The discharge time, this is a count of how many patients were discharged, and so it's much more uniform in nature, right? Or even for a single year, let's say that 1980, I wanted to see what is the distribution of patients over a month. So in that case, I can take the mimic3 data, I can filter, right? For discharge time, it's greater than this January of 1980, and the discharge time, which is lesser than December 31st. Okay, I can just plot the distribution over a month period in that case. Okay, so that you can see that frequency for a distribution for 30 days. So that's why you have bin width 30. Once you specify that, you can see the discharge time specifically for that particular year, and then you can compare with any of the years that has high number of discharges or the time spent, or low number of sorry, not time spent, discharges. Yeah. So those are the two differences between periods and duration. Duration gives you in seconds, whereas for periods it gives you in the human readable format, right? So what does this should give you? Years 1 divided by days 1. Is it 365 or 366? Because some of them have leap years and some don't, right? So that's when if you try to do this division, R will throw a warning saying that convert it into intervals. So that's why this whole intervals is designed to actually make these human interpretable intervals into more accurate form, right? So what you can do is an interval is a duration with a starting point that makes it precise, right? So to do an interval, you have to supply this. I mean, which is hardly, I mean, I wouldn't harp too much on using the intervals, but it's just a fact that you should know that there is already something's built in for more accurate analysis if you need to do it. So yeah, so that's about date. Any questions so far on dealing with dates? I think some of you might have had questions. Yeah, sorry, what's that?
Yeah, I have questions. I have the dates in my column, but for some reason, like it won't convert, and I just tried using what's in here.
Okay, all of them.
So
Okay.
I'm not sure. Does it have to be a character first? If it's an integer, will it not?
Um,
Does it matter? And how do I apply it for like? I feel like maybe it will work if I do like one section of the column, but it doesn't work for the whole column.
okay. So let's look at it after this class. Okay, so it should be. Let me finish this off. So that's about parsing the data and importing and dealing with dates and times. Okay, there could be dealing with, to me, dealing with dates and times is one of the most difficult things of doing data analysis. I mean, it could be, there could have so many different ways you can have time recorded in there, and so we have to really see what kind of a data it is to parse it. Okay, the next comes is tidying, right? So tidying, once you kind of imported the data, once you have all these time and things like that sorted out, the next is actually tidying. The same kind of data can be present in multiple columns. Okay, so the data can be present in several ways actually. So like for instance, the mimic3 admissions table. Okay, so there are two variables. If you consider, this is the emergency department registration time and emergency department out time. So they have, but then these two may actually, you can put it into one big class of timestamp in emergency, right? You can think of a larger variable that you can combine the smaller variables into a larger variable. Okay, so there is a useful function for it, right? So here I'm just taking the times. You see the registration time and the out time. You can think of combining these as a timestamp, and there is a special function called gather function. Okay, so in tidying up the data, there are several useful functions for analysis. So one of the analysis that you can possibly think of using your data set is like combining these meta variable into a bigger variable and seeing if there is a pattern in the data, right? So this gather function is very useful for it. So what it does is, if you have multiple columns, right, you can combine that column, right, into a larger column. Let me tell you with an example here. You have the registration time and the emergency department out time. Okay, this may represent a larger class, and this larger class is called a key usually. And here it's, let's say that this I'm denoting by timestamp in emergency. Okay, let's call this variable as emergency department timestamp, that I want to combine these two variables, right? So what we can do is we can actually combine this timestamp and we can gather data. Okay, so what I'm doing here is I have a data here. I'm taking this table and gathering the emergency department registration time, emergency department out time, and there is a key. I'm calling this as an emergency department timestamp, and the value is time. So once I do this, right, it takes these variables and puts it into columns here, right? It just puts it, it puts me into observation. So this table, right, you have these two times are now formed as an observation, right? This is another way of looking at the data, where you, instead of having it as as a column, you can have it as an observation, and you can have the emergency department time, and there is an out time. There are so many variables in here. So this is called data gathering. Okay, so you can gather the data and make it into a variable, right, and then work on that, right? So using this, for example, you can find the number of times each patient was registered in the emergency department. Otherwise, this information may not be, it may be difficult to obtain. Okay, so see, these are some of the questions that you can ask of, okay, what does it mean? And this is what I'm expecting out of the project, to actually find smarter ways of analyzing the data by combining the variables and doing some meaningful work. Okay, so spreading, there is another, spreading is an opposite of gathering. Okay, so when we have observations scattered across a multiple rows, we can spread the data instead of having it as an observation. Okay, so for instance, in the above set, the patient denoted by subject ID can have several hospital admission ID. Okay, so if you look at the data, a subject ID can have several hospital admission ID depending on how many times they were admitted in the hospital. Okay, so what spreading will do is, it will take the subject ID, which is the key column, and a column that contain multiple values for the key column, right? The values, the hospital admission ID, and it will spread it by putting it into columns. So instead of having it as a row, now you have it 94, 84, 85, 88, or now it's converting it into a column. So you can spread the data and then do some analysis based on it. So these are the two kinds of complementary things you can think of doing analysis. And this, we can immediately see that patient number 94 has 2 admissions in the hospitals, right? I mean, so you can see that he already has 2 admissions in the hospital. So gathering and spreading might be really important aspect of it. Another important function is what is known as a separate. Okay, so it pulls apart one column into multiple columns by splitting whatever character that appears. So for instance, in the admission locations, right, we have, it's a variable that made out of 9 possible values. One is emergency room admission. So it's transfer from the hospital, transfer from the other, etc., etc. You have 9 of these, and you may want to separate these, like based on it, right? So that's where the separation comes in. So for instance, here in the admission location, I can say, okay, change this into information 1 and information 2 by separating it based on the delimiter, the delimiter slash. Okay, so if I do that, you can immediately see that whenever it sees this separator, it's going to convert into 2, right? So this may ask, actually, without this information, if I ask you a question of how many patients were referred by the physician without normal discharge, you will not be able to answer it. But if you separate it, you will be able to answer it, because you can now group by and find the count of it. So this separation can be sometimes really useful, especially in dates, right? You may want to use the separator to actually take away only the dates and maintain the times and things like that. So the separation can be useful. One of the things that you can see that it will automatically coerce into character. Even if it sees a number, it's going to coerce as a character. So that's why I have something called convert equal to false. If you have convert equal to 2, if it is a number, then it's going to make it as a number. So there is an argument there. Okay. Similarly, unite is an inverse of separate. It combines multiple column into a single column. So for instance, in the above data set, we can unite hospital admissions ID and the admission type to tie a reason why a patient got admitted in the first place, right? So we can use unite. For instance, here I'm selecting the subject ID, admission ID, and admission type, and then uniting based on this separator. And you can see that there is a reason that is associated with each hospital, right? So this can be useful to unite the data. So there are 2 things: gathering and separating, which takes a column into a row and row into a column, and similarly you have separating and uniting that works with individual vectors, right? All right, so let's go into another important aspect of tidying the data, which is missing values. Okay, so missing values can be explicit and flagged with NA, or it can be implicit without the values absent actually. So let's look at this example. I have an influenza on 2015. I break each of this year into 4 quarters, 1, 2, and 3, and 4. And in 2016, let's say that I'm missing the first quarter. Okay, so there are only 2, 3, and 4. And I also record the number of sick people in each of these quarters. You have 800, 450, 377, and here you don't know the number of sick people, and these are the numbers for the rest of the right? You have these. Now there are 2 kinds of missing values here, right? So for instance, here in 2016, the first quarter is missing. That's an implicit. It's implicitly missing, right? And also in 2015, you have NA. This is an explicit missing. So there are 2 kinds of missing data, right? So there are ways that you can deal with this missing data, right? So first is, we can make the implicit missing value explicit, right, by putting the years in the columns. So for instance, here I can say that I can spread this data, right? So it is going to immediately put an NA in here, right? Because it's now converting the columns, right? Columns into row, right? So sorry, the rows into columns, right? So once you have this data here, right? If I spread this data, it's going to automatically put an NA in here, right? So I can make these implicit values explicit by doing this, right? There is another way of doing it. So what we can do is we can gather to turn explicit missing values as implicit. Like for instance here, I can spread this data and then also say that in 2015 and 2016, so you remove the NA and then just make this, gather this data and just keep the explicit value implicit. You don't really show it up. Okay, so the NA is not present in here. Or there is another useful function called complete. Okay, so what this does is it takes the data and then it looks into all the combinations, right? And then it completes the table for you. So here I immediately puts me that 2015 it's NA and 2016 there is a first quarter that's also missing. So it makes these implicit values explicit, right? By filling in the NA in there. And or we can use fill. There is another option, fill. What it does is it will take the previous measurement and then it will substitute. For instance here 377, it's going to fill in the same value here. So the most last observation will be carried forward. So these are the 4 important ways that you can deal with the missing data. Okay, let's look at one of the good case study. The book actually deals with one of the. This is a TB data in the World Health Organization, right? It can be downloaded. You can look at the data. The data is part of the tidyverse package, so you don't have to download it, fortunately. Okay, so you don't have to, you just type in who and you will immediately see that it's a table. They have nicely organized it. But what do you see when you look at this data? Yeah, right. Right. So of course this is a table, and you have, the first thing is that you have the country here, right? And you have AF, AFG. It's kind of repeated. So there is some code in here that's repeated in here, right? And also there are some variables called new SP, M0 and 14. And if you look at this table, you can see that new rel, right? So what do you do when you look at this data, something like that? When you download the data, you see it crazy, you don't understand it, what do you do? Try to understand it, right?
New SP, new specimen or something?
Yes, yeah.
Female, male,
Mm-hmm.
and then
Right.
patient ID 65.
Right.
Like 1,124.
Right. So yeah.
Combined together, so then
Mm-hmm.
you have to what?
Right. So it's a good guess actually. One of the things is that usually these kinds of data would come with a guide. Okay, so you look at the guide and try to figure out. I mean, that's the logical thing to do, right? The Haynes comes with a beautiful description. I mean, they have made I think it's one of the cleanest data set that I have seen. I mean, the way that it's been organized, it's one of the best data sets. But this, yeah, this is more or less, it's good to, I mean, if you look at the guide, you can see that it's much more, clear. So we look them up in the given dictionary. There is a dictionary given for these, so you look that up, and if you click on it, it's going to save this dictionary into your file. Okay, so I looked it up and I saw that ISO 2 and 3 are ISO standard countries, right? So there is a code for it. So in the first 3 columns, right, denote the old cases of TBs. So that's here it's all new, which means that it's all new cases of TB. Okay, so that's the thing that they said. And the next 2 letters describe the type of TB. REL stands for relapse, and EP stands for some kind of a extra pulmonary TB, and SN, it stands for smear negative. And there are some categorization of what this means. Okay, so and the data set group cases by males and females. So M stands for male and F stands for female. And there is a remaining numbers that gives the age group. 0, 1, 4 is 0 to 14 years old, etc., etc. Okay. So right. So the first thing would be we need to separate them, right? But before that, so one of the natural ways to do is count the cases. Each of them is a count number of new cases, right? So we may want to gather this data and put them all these columns into rows, right? So I form a meta variable called group and case count, and then we put it in here, right? So and then remove the missing values. So then I change all the groups in all these things that are there in the column, and I just put it as a row, so that each of them has this with the ID and how many cases are there. Actually, it's how many cases per year. This is a more natural way of looking at the data, right, than having that big table. So also we observe that for rel, we don't have an underscore for relapse, right? Whether for EP, we have an underscore, like some of these, right? If you look at the data, closely look into this data here, for relapse, for new relapse, you don't have an underscore. For EP and SN, we have an underscore. So we may have to separate those things out. So that is one of the things that we may want to do, right? So thus we need to fix that to get consistent variables. And there is something called string replace. Okay, so I'm not going to go over in detail. These are the things that you can figure it out. But the idea is to actually take this and make it consistent. Have this new relapse into new underscore relapse, right? And then you replace these count. Now everything is more consistent. And then we can now separate them into using the separate function, okay? So new type, and this is combined with gender and age. So you have sex age here, and it's separated by the underscore. So you have these now separated. You have all these new thing here, and you have the type of TB here, and the age and the gender are together, and then you have the case count, right? So we may have to actually, then there are ISO 1, ISO 3, these things that we may have to take it down. But before that, you can separate the gender and age, right? And this is separated just by 1. If you look at it, it's M or F followed by the group, right? So we can use separator equal to 1. That will just separate the first from the rest of the things, okay? And then you can look at and then remove all these redundant variables of ISO, new, etc., etc. And you have a very tidy table now to deal with, okay? So mimic, it's messy, but you can make it tidy, okay? So that's the message. There are so many functions in here. You can make it tidy, and then there are so many ways that you can look at the data. All right. So we have covered the two most important aspects of wrangling the data. One is data import, parsing, and the second is the tidying. And the third is actually even more exciting, and it's more fun now, because you have lots of things to play with. I mean, as I said, I'm throwing you away the Lego blocks, and you have to construct a good model out of it. That's when you can use multiple combinations of tables, okay? So usually data in the real world comes in different tables, right? How many of you know databases here? Good. After the next two classes, it's going to be databases, okay? There is going to be 3 classes full of databases, and we are going to go over the SQL and things like that in detail, okay? But this gives you an idea of how you can use a database kind of a thing in this tidyverse library, okay? So they have kind of mapped the SQL queries into what you can use for data analysis. So they made a self-consistent package out of it, right? So data in multiple tables, it's called relational data because it describes relations. And it's not just the individual data sets that are important. If you look at the not Haynes, in the mimic data, there are multiple data that has some key variables that are in common. Okay, so combining multiple data is an important part of the wrangling process, and these are facilitated by what are known as joins. Okay, in SQL it's called join database language, and it's the same here. Okay, there are three families of joins that are designed to work with relational data. Okay, so one is called a mutating join. Mutating join means you introduce a new variable based on presence of the data in the other table. Okay, so that's called mutating. The same language that's been applied when you use the mutate, you're introducing new variables, right? And there is something called filtering joins, in which you filter observations from one data frame based on the other data frame. And finally, there are set operations. So the set operations, they will treat observation of this as if they were set elements. Each table is a set. So you can take the union, you can take the, but this is, I mean, this is not that important, and it's really not important at all. In fact, I mean, in the sense that it depends on the problem that you are having, but most of the tables are different. So this may not be really handy as you may think, but these two could be really important. Like, so the variable that connects two tables are called keys. Okay, so if you have a variable that you found common across two tables, that's called a key. A primary key uniquely identifies an observation, okay, in its own table, and a foreign key uniquely identifies an observation in another table. Okay, so there are two important aspects of database. One is a primary key and a foreign key, and there is a surrogate key. Sometimes you may not have a primary key in the data, but they can be created. For instance, you can make a mutate and a row number, or you can combine some variables and form a surrogate key. Okay, note that a primary key can be a foreign key. They can be together. I mean, they need not be separate. So for instance, in our own data set, right, in the Mimic3 data set, we can look at which is a key by looking for using the count function, right? Like, one of the key is uniquely identifies an observation. If you have count of more than one, then obviously it doesn't have a unique observation. For instance, hospital admissions ID, right? I'm counting the hospital admissions ID, and then it's a table of 0 variable, so which means that it uniquely identifies, right, n greater than 1. So that could be a primary key for us, right? So for instance, here, subject ID, this is the patient ID. If I look for greater than 1, I get 729 numbers in here, right? So which means that a patient can have multiple hospital admissions ID. So this is not a primary key for us. So I'm just verifying if the subject ID is a primary key. It is not, but hospital admissions is a primary key, right? So we will, to describe joins, we will work with two data sets here, okay? And one of the data set is input events data set from Mimic3. Okay, so that input events are events that are given in the critical care, in the intensive care unit, fluids that are given, and either as an oral or tube feedings or intravenous solutions, and all that information are given in the input events. Okay, so there is a good description. If you can go there and look at it, there is a good description. So I'm importing that data set here, right? I'm taking this input events data set, I'm importing it and calling it as INE, input for input events, and downloading it as a table. So there are several types of join. There is a mutating join called an inner join. Okay, so you have two tables here, x1 1, x2 2, and x3 3. So this is a key for me, and there is another table that has 1 2 and 4, right? This is a primary key, and I can match 2 with 2, 1 and 1, but 3 is not matched. So this inner join takes the common ones, right? Based on the primary key, it's just going to show display all the common ones. So here 1 and 2, the 3 does not have any counterparts here, and so it's going to leave it, right? So in terms of our data set, right, the following code computes the inner join of admission. So you just use the keyword inner join. So I have the admissions data, and I already know the hospital admission ID is a primary key for me, it's unique, And so I can use an inner join here and find out all the patients who has been admitted or also in the given the critical care in the critical care data set, right? So that's how you join the tables. It's called inner join, which takes all the information, right? And there are other joins. There are three types of outer joins. One is called as a left outer joint, and this joint, what it does is it takes x1, x2, x3, and if there is not, if you don't find any observation here, right, it's just going to put that observation in there, right? I mean, it's just going to take all the ones that are in your left, and then if it's not finding any information, it's just going to put a missing value in there. Okay, so this is a left join. And similarly, you can have a right join, right? So it's going to take 1, 2, and 4, whatever that's found in the other table, and if it's not finding a counterpart here, it's just going to put as a missing value here. Okay, or you can have a full join, in which if you don't have any counterparts, for instance here the primary key does not have any counterpart here, and also the 4 does not have, instead you can just put 1, 2, 3, and 4 all the values in here and put NA and NE in here, the missing values. Okay, so these are the three types of outer joins. So for instance, in our admissions and inputs event table, right, I can do a left join, which means take all the admissions data and join that, outer join that with the input events data, right? The resulting is so the resulting value of a left join, right, would be the number of entries that are found in your left table, right? And also for the right join, the number of entries that are found will be the entries that are found in your right table or the second table, right? For the full join, you will have the combination, right? It will be the keys, the total keys that are found in both the tables here. So it's going to take the table and it's going to do a join. This is the left join. And similarly, you can do a right join, and you can see that the right join is much higher here because there are lots of values in the input events compared to the admissions data. And it's going to join, that results in lots of these missing values in here, which you have to tidy up, right? You have to tidy up. Or you can take the full join. That's going to give us a table of 19,000 plus 7,000 numbers in there, and then it's going to give you 24,000 table observations, and it's going to do a full join, and that's given by full join. Okay, this by default you have to specify here on what keys that you have to join, right? If you don't specify, it's going to use all the values and try to join. Okay, this is called a natural join. Or we can say that, let's say that here on one table you can have a key. The name of the key would be different in the other table. In that case, you can say that the key value of this name is same as the other name, and then try to join it. Okay, so it's going to keep the name, it's going to match the name, and then it's going to join it. Okay, so yeah, so these are the two important kind of joins, or three important joins in outer join and two important join in the or one important join in when it comes to inner join, right? And there is something called semi join. Semi join, what it would do is, if you have these observations here, you have these observations here, it's just going to filter the data. It's not going to do joining, but it's just going to filter. It's called filtering join. So for instance, here you have a 2 here, so it's going to semi join table 1, means it's going to retain all the ones in the table 1 that you have in table 2. So for instance, it's just going to give me only one table. It's not going to give me another table. Okay, so in our tables, if you have a semi join, this can be used to find all the observations that are there in the input events that are there also in admissions. Okay, so you have a very few numbers. See, 396. You know why it is so less? I was expecting I wouldn't even get this number, simply because if you go to the data, I took a random number. Okay, so I took it's a huge database. So percentage denote the percent of data available for analysis. So I took a random 1% data from all these tables. So I was thinking that I would not even get anything, right? It's a huge database. So what is the chance of one data appearing in the other? But fortunately, there are actually. So there is a good amount of data that you can analyze. Even if not, if you are not able to find it, let me know. We can try to get more, information or the data which is available in both tables. So, so this is semi-join, and there is something called uh, anti-join. Anti-join means that it will ignore whatever that is there in the other data table and keep the ones that is not there in the first table. Okay, so here x2, the 1 and 2 appears here, so it's going to retain only 3 in here. So this is very useful actually to find. If this would pull out, for instance, in our case, right, all the admissions table where it's not present in the inputs event table. So there are 5,000 entries, which is not there. Okay, which is not there in the input events. So these are all extremely important. Now you have a plethora of things that are available to work on your data set. Okay, there are about 28 tables in there. What is 28C2? It's a huge combination you can think of, right? Of trying to join and looking at the data. So joining tips, start by identifying the variables that form the primary key in each table. Okay, so it's important to see the primary key. This is usually done by understanding the data set, okay, not just empirically looking for the combination of variables. Just look at the data set and try to see which could be your primary key. So we might find a combination that is unique to our data, right? But then they may not be useful for, like for instance, you can take two date variables or two time variables, date and time variables, but they may not be, that may not really mean anything. But having said that, in our case, a patient and the admissions can go together actually. That can give a very meaningful insight, just having instead of patient associated with the hospital admissions, how far a patient comes to the hospital again, right? So those could be important statistics that you can fetch by combining the patient ID with the hospital ID, you know. So if you want to derive patient statistics and say you can combine these two and form a primary key, okay. So this can help, but it may not help all the time, right? And there is another way. You check none of the variables are in the primary key are missing. So these are some of the important tips that you can do to identify an information, because if there is a primary key missing, you can't do anything about it. And you can check if the foreign keys match primary keys in another table, right? You can try to do it with anti-join, right? It's common for keys not to match because of data entry errors. Fixing these will often require lots of work. And if you have missing keys, we need to be really careful on what we have to do, of how we are going to deal with the data, right? This could be a very important aspect of doing data analysis. So with this, I will leave the wrangling portion. I think we covered almost extensively on wrangling data. The section 14 and 15 are strings and factors. Okay, these are not really important. Well, these are not anything related to the analysis with the tables. It's more how you manipulate the strings and how you manipulate the factors. Okay, so I would let you read about these two things, but from what we have covered so far, you should have lots of things to work with analysis. Okay, so you should have tons of things that you can do data analysis on. Now, that's what I'm expecting out of the project, to have a comprehensive analysis based on all these things. Okay, so the better you show that you try to do these things. It's, I mean, sometimes insights can be difficult to obtain, and I realize that, but the fact that you have put in work also matters. So if you're trying to do something, document it. Okay, so that's important, and documentation is a very important part of this whole course that I'm emphasizing. Okay, I'm not asking you to come up with stellar analysis. You know, it's very difficult. I know that exploratory data analysis could be one of the toughest jobs, but but I want you to I want to see that you have put in lots of effort in trying to understand the data. So I'm expecting more communication through programming, right? Recording, whatever. I mean, it may not lead to an insight, but just put it in there, like, this doesn't give an answer. I mean, that's a perfectly acceptable thing to do, but it would tell you that you have put in effort on that. So that's what I'm expecting out of it. And this matters tomorrow if you're going to a job. It matters that you show you have worked on something. So it's optics is as important as doing the job. So make sure that even if you don't get insight, it's fine, but make sure that you put in whatever that you have worked on it so far. Okay. All right. So let's stop with this for today.